Hello everyone, I'm Jose Wesley and today I'm going to present you the work Automatic Inspection of Program State for debugging and verification purposes. Currently, I'm pursuing a master's degree at the Federal University of Minas Gerais in Brazil under the supervision of Professor Fernando Pereira, and this project is being conducted since the beginning of 2020 and we are working in collaboration with Dr. Chunhua Liao, a colleague from the Lawrence Livermore National Laboratory from the United States. The goal of this project is to develop a new technique that is capable of reporting the state of a program. But what is this program state? The program state is formed by the values that this program manipulates. Such values are stored in different memory regions, like stack or heap, or in statically allocated memory, like global variables. The ability to inspect the values that form the state is useful for many reasons, like debugging, data visualization, and program verification. However, it is difficult to correctly identify these memory regions in type unsafe languages. In the garbage collection community, those languages are known as incomparative. C, C++, and most of the assembly dialects fit into this category. Given the scenario and the fact that, although important, efficient is not the main concern in this context, we propose a new approach to report the internal state of a program. We develop a static transformation that inserts in a program the necessary code to report its internal state. It's a fully automatic solution and is a customizable tool. A user can choose which functions and memory regions will be inspected. We shall see that this decision impacts in the overhead imposed by our technique. We implemented in LLVM. Our solution reports the state based on verification routines that we call inspection points. A static inspection point is a point after a state of a program. It's a source code line where the state can be proved. In this work, we insert these points in the exit points of the functions. When a program runs, we have the dynamic inspection points. A dynamic inspection point is a static inspection point plus the calling context in which that point executes. Notice that a single inspection point may yield several dynamic points. The set of the dynamic points traversed during a program execution form an inspection trace. An inspection trace is a testament to the execution of a program given an entry. Let's now show a program example function by function. In this function create, we can recognize one inspection point, marked as A, right before the return statement. Next, we have a recursive function called incAll, which traverses a list performing some side effects on its nodes. Here we have two static inspection points, B and C. Finally, we have a main function to call the other two, and here we have another inspection point marked as D. If we run this program as main A, the following inspection traces will be constructed. First, we have two calls of create at line 27 in main. Two dynamic inspection points are created from the static point A. In a similar way, we have this trace of recursive calls of incAll until we reach point C, and a trace corresponding to a call of create at line 18. At the end, we have the following inspection traces that form a visual description of the full execution of this program with the string A as input. Let's take the inspection trace 4 as an example and visualize the program state snapshot produced by our technique. Again, this trace corresponds to the first call of create at line 18. First, we can inspect the values that reside on static allocated memory. In our example, the global variable none_nodes, which contains value 3 at that time. The variables on the stack are also inspected. In this case, the arguments data and next, plus the pointer p created at line 9. Notice that p and next are pointers and that they actually do not point to stack or static locations. They point to data in the heap. But we are capable of retrieving these values by traversing the heap, like a tracing-based garbage collector does. Due to this ability of traversing the heap, we can reconstruct sparse data structures, like lists and trees. We have conducted an experiment to investigate what is the impact of our technique in the running time of the programs. We evaluated our technique in 4 benchmarks that make use of stack and heap allocated data. BST, a binary search tree, fact, the non-recursive factorial function, linked, an implementation of a linked list, and KeyAS, a program that solves a series of quadratic equations and stores their solution continuously in the heap. This figure reports the overhead of 2 modes of inspection. In the first, we track states of variables allocated statically or on the stack. In the second, we also consider heap allocations. Within each mode, we can instrument the return point of every function or only of the main function. Each benchmark was executed 10 times, and the figure shows the average running time. The values in black boxes correspond to instrumentation overhead. For example, KeyAS, with inspection points in every function, tracking every allocation, is on average 3,925 times slower than its original version. When we inspect on the local variables of each function, this number decreases to 1,678. Our technique does not impose an overhead in BST when we inspect only the local variables or when we inspect only the main function. As you can see, the average overhead varies with the granularity of the instrumentation. When only the local variables are inspected, the overhead reduces in the majority of the benchmarks, due to the fact that the heap is not traversed at the end of each function call. This figure shows that inspect only the main function reduces even further the overhead. This mode of instrumentation is useful, for instance, to add verifiable output to benchmarks automatically produced. And although the overhead is huge in some cases, this is a work in progress, and there are many opportunities for improvement, which we are already engaged on it. So that's all I had to present today. If you get interested in this work, please get in touch, and thanks everyone for watching it.